floods of lava and water. Here's the opening statement. Eastern Washington geology is a unique place, and it's unique for two reasons. We had floods of lava roughly 15 million years ago, and we had floods of water during the Ice Age 15,000 years ago. That's a very simple, nice, tidy statement. And like most things in this science, it's not that simple. There's way more going on. But that's the main thing that we want to get across to you tonight. Most of you know much of this, but I'm hoping to add twists and turns here along the way. So let's start with a map of Washington. And I think I'll try to keep track of some of the stuff we're talking here as well. So, floods of lava 15 million years ago, floods of water 15,000 years ago, much less than 1 million years ago. All right. When people hear that Eastern Washington is full of lavas, and if they don't know much geology, I think they do their own little math and they think, okay, well, there's lavas and we have volcanoes in Washington. We have the Cascades that we were talking about last week, right? So they do their math and they go, okay, well, yeah, that's kind of interesting. There's a bunch of lavas out there in Eastern Washington. They must be related to Mount Rainier, Mount Adams, and that sort of thing. No, that doesn't work at all. For sure not. Absolutely not. And the reason is chemistry. Magmas around the world, in other words, lava flows around the world, have different chemistries. And the thing that we focus on with a magma's chemistry that's most indicative of their physical properties is something called silica, which is a combination of two elements that the Earth is loaded with, silicon and oxygen. So silicon and oxygen together is silica. And if we have a magma that is 45% silica, it's very runny. If we have a magma with up to 75% silica, it's very, very sticky. It's very stiff. So the reason I bring this up is that the magmas that come out of the ground and erupt in the Cascade Corridor, the whole whack-a-mole story we were talking about last week, those are 60% magmas. Those are relatively stiff magmas, and that's why the lava flows did not come out of Rainier and start flowing all the way to the ocean. In fact, they didn't leave the national park. Those are andesite lava flows primarily, but there's some daceites and rhyodaceites, things like that. The lava flows, I gave the punchline away. The lava flows in Eastern Washington are not 60%, they're 45%. And the rule is the lower the silica, the lower the viscosity. In other words, the more runny the material is. So what does 45% lava look like when it comes to the surface? So if here is a person innocently walking around and suddenly he realizes he's on top of a big active magma chamber and there is 45% silica magma, that's the runniest possible lava we have in nature. And so if that person is stubborn and refuses to leave, he is going to be harmed because this is lava flows that are flowing very easily across the surface. The first major point then tonight. We have lavas in Eastern Washington. The chemistry does not match the Cascades, so the lavas did not come from the Cascades. Where did the lavas come from? The lavas came from a series of cracks. We call these cracks fissures. And the fissures are located in extreme southeastern Washington. Tonight, we're going to focus on the fissures and talk about potential ideas for why those fissures are there. Because 17 million years ago, a little earlier than 15, 17 million years ago, these cracks mysteriously appeared. And they weren't minor structures. Coming out of these fissures, in other words, these fissures literally were tensional cracks. So they literally opened up, and coming from these fissures were unimaginable volumes of magma. And because of the low silica content, the magma started cooking, started traveling, started going county to county to county. And ultimately, many of these lava flows literally made it to the Pacific Ocean. So most of the attention is given to the basalts themselves, and we want to start with some basic observations of that. But what I really want to do with the basalt part of this, and that's how we get into some plate discussion, is try to figure out why 17 million years ago, why cracks emitting basalt. By the way, if you know about the globe, basalt is an oceanic lava. Where do you find this runny 45% silica lava? You find it in Iceland. You find it in the Galapagos. You find it in Hawaii. You find it in purely oceanic settings. And yet we have these oceanic lavas coming out of our cracks here. It's a mystery. And I'm not presenting it as a mystery just for us. It's still a mystery. We're not going to solve it tonight. I got to admit that. And some students are very bothered by that. We're doing all this work, we're doing all this talking and drawing and note-taking, and then we don't even know the real answer. So I have to say that up front. And like we do lots of times with our gatherings here, I like to model where the scientific community is and realize there's always work to be done in the future. So that's where we're headed. Let me give you a little bit more basic stuff, though, about these lava flows. More than 300 of them. I suppose I had a draw. More than 300 of them came out of those cracks. And I'll show you plenty of photographs coming down the road. For instance, if you go over to Vantage and you cross the Columbia River, stand at the Ginkgo Petrified Forest Visitor Center there and look at the nice, beautiful display and look across the river, you see these steps, right? Each of these is a separate lava flow. And we never really do see all 300 lava flows at one time. That's a concept that's difficult. We have lava flows crossing the state, but the depth is enormous. If you take these stack of lava flows and realize how much quantity we're talking about, how much mass we're talking about, in most cases, this basaltic region is more than 2 miles deep. The drilling for oil and natural gas recently has shown us that we go 10,000 feet into the earth in this volcanic province, and we're still in basalt. I mean, what's the elevation of the Tri-Cities? Less than 1,000 feet, right? Above sea level, and yet there's 10,000 vertical feet of basalt. So we're below sea level by a long margin with these lavas themselves. Each flow is the height of this building on average. So if we go to Hawaii, a place where we can understand how this process works. It's the right chemistry. It's the right physical properties at a small scale, but the Hawaiian lava flows are knee-high and travel just a couple of miles. These individual flows are 40 feet high and travel 300 miles. The scale is way off the charts. Interestingly, and I'm just setting you up now for our plate discussion, the magma's content truly is 45% silica. In other words, it's pure oceanic magma coming to the surface here. And that's a big point because lots of times when you have magma forming beneath a continent and you have the magma getting to the surface and erupting, usually the magma is contaminated on its rise. In other words, beneath the Cascades, there's originally 45% silica magma, we're pretty sure. But by the time that 45% silica magma gets to the surface and erupts out of Mount Adams, it's 60%. Because it's taking blocks of continental crust, which have lots of silica, melting the continental crust, we're basically contaminating the magma, changing the chemistry so that by the time it gets to the surface, it's stiff. Not so with this stuff. It's coming from depth, we believe, but it gets to the surface and it's still as pure as it was when it was at the base of the continent. So what am I really trying to do? I'm trying to get you to think. I'm trying to get you to creatively think about ways to explain this bizarre set of circumstances. And if we had 3 hours, we'd open it up and we'd have all sorts of different ideas from you. And we might get that when the question and answer session comes around. But what I want to do, just for time's sake, is once we lay this out, share some of the ideas that are out there in research groups to try to explain what we have. Okay, so many of you have heard this before. Lots of basalt vertically, lots of basalt laterally, a repetitive sequence. let's break some new ground. That's a pretty simple picture. We're now realizing that these cracks did not all form at the same place at the same time. So the plot thickens. Not the lava. The lava does not thicken. The plot thickens. I've got some images a little bit later on to show you this. This is pretty new information. In the last 5 years, there's a couple guys who have found fissures down in southern Oregon that are truly 17 million years. Then slightly younger fissures in northeastern Oregon, slightly younger fissures in southeastern Washington, slightly younger fissures even into central Washington. So we have to explain that. Not only that the fissures are forming, but that they are migrating north, or these cracks are opening in sequence and essentially zipping to the north. We've got issues there. I'm pausing because it seems like I can set this up a little more creatively. And I don't want to do that. So here's what I want to do now. Okay. Okay, you want to hear a secret? I got home. You do? I came home at 4:30 today, and I was tired. And supper was not ready. And so I laid down, and I fell asleep. And 45 minutes later, supper was ready, and the food tasted really good. And I'm still kind of sleepy. But I promise to fully wake up before we're done. In fact, yeah, I just promised that, okay? In front of God and everybody, I just promised that a thoroughly wide-awake person, my hair is still a little not right, but we'll get that all going just perfectly here. Some of us know a fair amount about plate tectonics of Western North America, others not so much. How are we going to do this? Let me give you a basic crash course, and then we'll go back to these fissures and try to explain them, and ultimately bring them in living color here in just a bit. Quick plate map, familiar to many? Oh, I should do that in a different color. So veterans of this series know that that's Washington, Oregon, and California. New people are like, how'd you know that? Well, we've been around. We know what we're doing. So we have a beautiful, small oceanic plate off the shore of Washington and Oregon called the Juan de Fuca Plate. In a different color, we have further to the south a different plate moving northwest, the Pacific Plate. And in a third color, we have all of this, part of North American continent, moving to the southwest slightly, the west-southwest, the North American Plate. We have, in past lectures this fall, looked at evidence for how we know this is happening, how we know this is happening, how we know this is happening. We have measurements now using the GPS network to document this beautifully. We also have geologic evidence, and this is review from a couple of weeks ago. We have a hot spot underneath Yellowstone National Park, which is here. And trailing away from Yellowstone is a vast volcanic province called the Snake River Plain that stretches across southern Idaho. And if we look at the age of volcanic rock on the Snake River Plain, the rock gets progressively older. So hang with me. In Yellowstone Park itself, I'll still do this in red, less than 1 million years old. Just north of Pocatello, about 5 million years old. Between Boise and Twin Falls, about 10 million years old. Getting down into northern Nevada, about 15 million years old. Are you thinking? Eventually we run out of the Snake River Plain. We run out of this volcanic path. And guess what the age of the oldest volcanic material is in this swath? 17 million years. Now let's put on this map those guys, which are in the neighborhood of 17 million years old, which have produced our Columbia River basalt field flooding eastern Washington, some of those flows getting to the Oregon coast. Now, up until 2 years ago, in my Geology of National Parks class, we would talk about the basalts of eastern Washington, even though there's not a national park there. We'd talk about Yellowstone Park and talk about the hotspot track, and we realize that the timing of this hotspot track in Yellowstone and the timing of this, the fissures of the Columbia River basalt field, we realized the timing was next door to each other. But we couldn't quite see a connection, a physical connection, between what's going on here and what's going on here, until that migration of fissures that I just quickly mentioned here, that stuff that came out of a Vic camp from San Diego State in the last 2 years. So let me plot that on. These fissures didn't all form right here 17 million years ago. The fissures 17 million years ago formed in southeastern Oregon, slightly younger, and by the time we get up into the fissures of central Washington, we're to about 14 million. So there's a 3 million year transition time between the fissures right down here by the beginning of this hotspot track and what's going on here. So here is a quick actually, you know what? I'm feeling experimental. Remember this gesture? I'm feeling this. Who's got some ideas?
Stretch marks.
Suddenly, this is an anatomy and physiology class. Would you care to elaborate? Hands down here. Yes?
We've talked about migration of Mount Stewart baffle going north. Does that correlate?
Okay, so I'll take kernels of these contributions and kind of run with them if you don't mind. So we've learned way back that we have terrains that have come in off the Pacific Ocean. Remember this? Pieces of crust that were made elsewhere and added to the edge of North America, including Mount Stewart. And there's a very clear boundary between where we had old-fashioned North America that was not terrains and these pieces of things that came in. That boundary between the stuff that came in and old-fashioned North America is right down our fissure zone. Is there a connection? This history of the terrains coming in. I'm going to list these and then go back to the list and ding each one of them. Because again, we don't believe any of these wholeheartedly. There's problems with every one of these ideas. Different approach. Yes?
Well, since you said, I don't know if I can explain what I'm trying to think about.
Give it a try, Marty.
All ocean, and Washington, Oregon didn't exist when it was
Right?
like that in the 80s, right?
Yep.
So these things are forming under ocean anyway until they get above the ocean, and then they go in, and then we start getting our little gumballs.
Okay, so Marty is talking about kind of the same thing here, that there was a time where Washington didn't exist, Oregon did not exist, and it was deep ocean water here. And Marty's saying, well, we had a deep ocean history here, so is it that surprising we have all this oceanic lava? That doesn't work. It's good. I see the logic, but it doesn't work because the dates are not supporting you. All of Washington has been assembled, all of Oregon has been assembled by 50 million years ago. This is much younger than that. So we have brought everybody in. So we're wondering if it's related to terrains because we realize that Washington and Oregon have been assembled, but we're still wondering about that old boundary between terrain and old North America. Let's keep it going here. Yes, ma'am? Yeah.
The crust was closer to the subterranean.
Are you thinking the crust is thinner here? Or are you saying something else?
Because it's been filled in with a lava flow. With
Okay.
and the crust of
So here's a great example. I promised that I would take a kernel of what a suggestion was and just run with it. So I'm going to put words in your mouth now. You ready? Not even close to what you wanted to say here. But I like the initial thought, and I appreciate you for that. That's what you meant, right? Meteorite. There's a roadside geology series. Have you seen them? They have yellow covers. Roadside Geology of Washington, of Oregon, etc. They're all written by a couple of guys from the University of Montana. Their pet theory is that a meteorite, a piece of extraterrestrial material, flew through space and 17 million years ago struck North America right here and wounded the crust and was a severe enough impact that flood basalt started coming up at the point of impact and literally flooded the crater and any evidence that we would want for that to happen. So there is question about the thickness of the crust here. Is it unusually thin, unusually thick? And there's geophysical data that's not conclusive, it seems to me, from this particular area. So I twisted that a bit. Sorry about that. Yeah?
You showed in some earlier lectures that there's a rotation in western North America that trees spreading in the area where those fissures are.
Good. Let's use that. Thank you for that. 2-3 lectures ago, we talked about a clockwise rotation that is currently going on in the Pacific Northwest. GPS stations showing us that this is real. And our earthquakes in the Pacific Northwest are a direct result of this clockwise rotation. This gentleman's bringing this up because, I didn't draw these arrows very well. The thought is, and again I'm putting words in your mouth, if we're rotating the crust, we're rotating it away from something that probably is being extended, right? If we're pulling this block away from the Rocky Mountains generally, what's happening behind that clockwise rotation? Is that helping us understand these cracks? Another approach. What's the Juan de Fuca plate doing? What's generally the Juan de Fuca plate doing? It's subducting. Is it possible? Is it possible that these lavas coming out of these cracks are related to the subduction of the Juan de Fuca plate? We know that the Juan de Fuca plate is subducting to make the cascades. What would we have to do to the Juan de Fuca plate itself to have it not feed the cascades for a while and feed these fissures? What would be different about the Juan de Fuca plate itself? Speed it up, but we could also play with the angle of subduction. In other words, here's a different diagram unrelated to what we're doing here. If we have subduction that is steep, we're going to feed volcanoes there. If we then decide that we're going to shallow the angle of subduction, suddenly our volcanoes are going to be further inland. Do you see that rationale? So possibly 17 million years ago, the Juan de Fuca plate was not subducting as steeply and was subducting more gently, and the result was this volcanism further inland. Anybody else got a crazy idea before we go?
What speed in the plate?
How would that?
If you were to increase the speed of your plate,
Okay.
then the possibility would be that hot spot would have been further to the east.
Okay. Ray is wondering ultimately about a connection with the Yellowstone hotspot. And we haven't learned much about hotspots, but let me try it quickly. Hotspots are fixed, stationary sources of heat from deep in the earth. Think of it like a big blowtorch that in a welder's shop. Okay, just get your goggles on, a acetylene blowtorch. Okay, so let's hold that torch steady. That's our hot spot. Where the hot spot is in contact with a plate, it's going to make a volcano. It's going to make an active volcanic scene. Now, if the plate is not moving, we're going to have nothing but an erupting volcano at this knuckle of my hand. But if we slowly are moving our plate over this stationary hot spot, we're going to get a trail of volcanic lavas, and the age pattern of that trail is going to be apparent. In other words, we're going to have brand new lavas here. Now if we start moving the plate, we're going to get younger and younger lavas as we trail off in this direction. So Ray knows that North America is moving in this direction. Why? Because he actually sees the arrow in the labeling. Good job. And he knows that as we drag over this stationary hotspot, we're going to get this whole track of material. The main point is, where was the hotspot located 17 million years ago? It wasn't in Wyoming. The hotspot was right here. So we're wondering about these fissures. The fissures are forming starting down here about 17 million years. Okay. There might be other ideas, but I'm gonna move on. Thank you for that contribution. That was fun. Problems with each of these. The terrain boundary is here. In other words, the boundary between terrains and old-fashioned North America, but there's no sign that that's an active region. And there's no geophysical idea that there's any sort of space or any sort of magma that has dealt with this boundary. In fact, we don't find any young lavas or even lavas from 17 million years at other places along the boundary. So there's just not enough good physical evidence to think that that boundary has anything really strongly supporting this. Evidence for the meteorite impact, just to say it's all buried beneath the basalts isn't quite good enough, is it? To really wholeheartedly believe an idea, we need to have a lot of different kinds of evidence all pointing to the same conclusion. The rotation idea. I agree that we have rotation. I agree we have extension behind. But here's something I didn't mention before, but implied, I think. These fissures are no longer active. In fact, these fissures have not produced one drop of lava in the last 6 million years. And really, it's been quiet for 12 million years. So if this rotation is part of why we have these fissures, why don't we still have basaltic volcanism in eastern Washington? The rotation is current, in other words, and yet we don't have activity with the fissures themselves. Subduction related, kind of a nice idea. Flatten out the subduction, feed these volcanoes. But our opening statement was, the Cascades have 60% silica. These volcanoes we're trying to explain have 45. And generally, when you subduct ocean crust beneath continental crust, you get 60% silica magma. So these are the wrong kinds of volcanoes coming out of these fissures, having them being related to subduction. I'm a guy that likes number 5. And I'll expand on this idea when we get to the slides. But the general consensus right now is that when the hotspot began, and that's a whole nother discussion, why did the hotspot start 17 million years ago? Why didn't this Snake River Plain thing continue all the way to the coast, for instance? It doesn't. It abruptly stops. This volcanic age progression stops in northern Nevada 17 million years ago. Okay, let's take that at face value. When this thing started, there was a broad regional head to the hotspot. In other words, when it started, it didn't have its act together. And so there's a regional scene of volcanism 17 million years ago, and then as North America starts moving over it, we kind of concentrate the torch a little bit and narrow the gauge of the torch so that we're actually carving a very, very clear picture here. There's more on that coming in a second. Even that has problems. Geophysically, and I don't know much about geophysics, but people have been running seismic surveys through the Snake River Plain, looking at what's going on at depth in the crust. and they're not seeing significant patterns of a hotspot coming through. I can't give you any more than that because I don't know much about that. What I do know about is field geology. And I'll bet you less than 5 people in the room know this right here. I don't know much about it myself. From this area in northern Nevada, where the Yellowstone hotspot began, is this beautiful younging of lava towards Yellowstone Park. We get that with a stationary hotspot and a moving North American plate. Researchers mainly at Oregon State University have now found a mirror younging of lavas towards Bend. 17 to young. I don't know about 0, but young. Let's say 5. Now, how do you explain that? If you like a stationary hotspot and a moving plate, that works beautifully. This appears to be disagreeing with that. If you're a regional hotspot head person and then have movement rippling away, not only the fissures are moving away, but the rocks themselves are moving away, that's a whole nother elaborate story. So I have some diagrams coming in a bit to add to that. Okay, we're setting up the images. On top of all of that, coming 15,000 years ago, is a story that is familiar to some and not so much to others. So I'm going to do it quickly. Ice Age flood story in 10 minutes. Ready? Oh, we've spent hours in the field with many of you, evening lectures up on campus, endless discussion, 10 minutes. Okay. So this is geared for people who have never heard this story. And if you have heard the story, maybe I can toss in a couple new things for you. Washington, Oregon, Idaho, Montana. Let's put in Ellensburg and Seattle and Spokane and Portland and Missoula. So this story takes place less than 1 million years ago, hovering around 15,000 years ago. Although it's clear now that there were multiple floods across eastern Washington, and they have many ages hovering around 15,000. But that's the rough ballpark. This is a time when we still have ice on this map. We have an ice sheet, in fact, that 15,000 years ago is slowly starting to melt and is still melting today. It's on Greenland now, but it was once, that ice sheet was once large enough to be into the northwest here. So this is a retreating ice sheet 15,000 years ago, a melting ice sheet with a lot of meltwater coming off the front of the ice. Now normally there's not much of a story because the water coming off the ice drains to the ocean and nobody writes anything up. But there were a couple of lobes of ice that played a part in our drama here. A lobe of ice, like an earlobe, is a little bit further south than its neighbors. So this is the Okanagan lobe, which some of us saw in September, up on the Waterville Plateau. We didn't see the ice, but we saw the evidence for it. The Purcell lobe, which came down towards Sand Point and Lake Pend Oreille in the panhandle of Idaho. This is the key part of the story. Meltwater coming off the front of the ice in Montana was trapped, was not allowed to drain to the ocean because of this ice dam. So there was a temporary lake, present-day Missoula, Montana. Significant amount of water filling many of the valleys of western Montana. Could not get to the ocean where it needs to go because this glacier was blocking the outlet. Finally, we get enough water in the lake where we breach the dam. And the water dramatically crosses eastern Washington in individual flow fields. In other words, it wasn't the big continuous wall of water thundering across the eastern Washington landscape. Instead, it was individual fingers of floodwater, and in between those fingers of floodwater, completely untouched by the floods. So one really interesting thing about the landforms of eastern Washington is, and you'll see this with the images, you can easily see, if you look for it, where the floodwaters hit, but also where they missed. And where the floodwaters missed is incredibly graceful, delicate landforms. Think the Palouse Hills. Hills made out of kitchen flour, basically, that would have been swept away at an instant if it got hit by the floods. But yet those very graceful hills are still intact between the floodwaters. There was a ridge, there is a ridge between Ellensburg and Vantage. And that ridge saved Ellensburg from these floods. We did not get any Ice Age floods in Kittitas Valley because of the ridge up at Whiskey Dick with all the wind turbines now. Ryegrass Summit, you know where I'm talking. So we have dramatic flood evidence on the Vantage side of that ridge. We have no flood evidence on the Ellensburg side. Ultimately, that floodwater is all trying to get to the ocean now. It's happy water now. It has gotten away from Glacial Lake Missoula. It's traveling up to 50 miles an hour across the openness of eastern Washington. But it's not a nice clear shot to the ocean. There are some constrictions to deal with. This is a recent enough story that the ridges that we know, the opening to the Columbia River Gorge that we know, were pretty much the way they were then as they are now. So Wallula Gap down by the Tri-Cities was a problem. The entrance to the Columbia River Gorge was a problem for this water. And by problem I mean it couldn't maintain its 50 miles an hour speed all the way to the ocean. It had to slow down, and the water had to wait its turn to squeeze through some of these bottlenecks. As it slowed down, stuff it was carrying started to drop. So we have not only scars where the floods were taking material away, but we also have, all through eastern Washington, places where the stuff that the floods picked up were dropped. Most obviously, big boulders out in the middle of a field. Show you photos. But less obviously, fine-grained layers of flood deposit that were only being deposited where we had more lake formation. So much of the water that cruised across eastern Washington and picked up material dropped much of that material with this second lake that formed as the water was waiting by Tri-Cities. So this is Glacial Lake Missoula. This is Glacial Lake Lewis, which backed up into the Quincy Basin, backed up in many places that we have here in south central Washington. There's a third glacial lake if you really want to dig deep. Up here, upstream of the Okanagan ice lobe, we have another ponding of water, Glacial Lake Columbia, that also has lake deposits and feeds into, at times, Moses Coulee, where some of us were this past weekend. So, this is not particularly helpful. That's why I have the images. But the story, eventually, we finally get rid of all of this water. It goes out to sea. And the debate now is not, did the floods happen? Everyone in science is fine with that. And the debate now is not, was there one or two floods? The debate now is, how many floods were there? And we have people that believe there were up to 100 floods, 100 separate glacial Lake Missoulas, 100 separate big bursts of fast-moving water across eastern Washington. That's the next challenge. And we have researchers working on this to try to continue to figure out the details of the story. There was one flood of a glacial lake that was in the Salt Lake City area in Utah that ponded up water along the Wasatch Front, flooding and burying present-day Salt Lake City. And eventually, there was enough water in that lake to drain north into southern Idaho and have all of that water follow the Snake River, which was a canyon at the time, and have that water come up into Washington, basically follow the Snake most of its course, and have floodwaters squeeze through Hell's Canyon and get into our Columbia finally, and have Bonneville floodwaters coming down the Columbia River Gorge between Oregon and Washington. That was 15,000 years ago. One flood, one shot, 15,000. So we have some Missoula floods that were a little bit older than the Bonneville. We have some Missoula floods that were younger than the Bonneville. And in some cases, especially in Hell's Canyon, you can find both flood deposits in the same spot. And Missoula are sitting on top of Bonneville. Okay, Chase, let's hit the lights. Many of these photos featured tonight are from a guy named Tom Foster, who grew up in town, son of Barbara and John Foster. John was a communications professor. Tom actually was the reason we started the Ellensburg chapter of the Ice Age floods. He works for Twin City Foods and got real interested in this story. And he has a gift for photography. So I want to share many of his images because his images show not only the basalt, but the Ice Age stories as well. Tom now works in Pasco, but is still involved and has created a beautiful website if you haven't seen it yet. I'll probably send a link to that next time around. Okay, so lava flows first. 1, 2, 3, 4, 5, 6, 7, 8 lava flows here just in this particular picture, but that's not the whole stack, right? 300 all together. Next one, Bryce. If I call you Eric, don't be offended. Okay, great. So Ellensburg is here. Here's our beautiful map showing the distribution of the basalts that are dominating eastern Washington. If you believe this guy Vic, in the last 3 years, we're going to extend this brown down into northern Nevada and help us connect this with the track of the Yellowstone hotspot. Next one, buddy. These are some of the fissures, the cracks that have been mapped, found, that have fed our lava. So this is from Vic last year, and so he's showing the Columbia River basalt field literally extending down to northern Nevada. Next one. These are what we want to visualize then for the fissures, for the cracks that are feeding all of this lava. Next one, Bryce. This is 17 million years ago. Oh my God, we've got a fissure forming, and we have low viscosity magma coming to the surface. And we don't want to visualize a Hawaii volcano. We want to visualize a fissure-style eruption with a long line of lava coming out. Eventually that cools, hardens, everybody's fine. Wait a few thousand years for the next one. So these eruptions are not every day of the week. There are clearly thousands of years of quiet between eruptions. But for whatever reason, we have another eruption. Maybe we completely evacuate the magma chamber. Maybe there's so much magma coming to the surface that it takes a while to replenish the plumbing system. But we eventually get another scene. And notice what we're doing to the topography. What was rugged is now a little bit more flat, right? We're creating a flat landscape. I'm not happy with the focus there, so I'm going to let this thing keep going. There's debate about how long each flow lasts. We're probably talking about days to maybe a couple of weeks, Marty. That's the conventional thought. Okay, this is going to get good. Now, we've flattened the landscape enough so that the succeeding lava flows have the ability to really cover some ground. Excuse me, and those are the Grand Ronde lava flows. Some recent photos from Tom. Some of these locations I do not know. I believe this is still Palouse Canyon, downstream of Palouse Falls on the way to Pullman. Next one. I can't emphasize enough, these landscapes are from 2 freak shows, right? The freaks of lava, which don't happen very many places in the world, and the freaks of Ice Age floodwater. What are the odds to have both of these hammer the same area? That's why this is such a unique place. Next one. Oh, pretty picture. Wow. Oh, wonderful. Nothing to do with geology. Next one. Look at Washington now. So, rugged topography in the Cascades and in the Okanagan. Oh my goodness. Has it always been like this? No. The flood lavas themselves have filled the low spots and flooded the landscape literally with lava to create a horizontal landscape. Next one. So you know this scene over at Vantage. Next one. You know this scene at the Gorge Amphitheater. I'm sure you all go to rock and roll shows over there. Did you see Soundgarden last time? Oh, they were great. And above the tour bus, still 3 separate lava flows. Next one. We all know this, south of town, still these guys. These are some lava flows. This is halfway in their journey. Think of this now. Those lava flows in our canyon are halfway between where they came out and the ocean. These are Grand Ronde lava flows. Spectacular. Next one. More spectacular shots from Tom Foster. We all know that some of these lava flows naturally form columns, and those are cooling structures. Next one. Beautiful, repetitive columns. But as you get to know these lava flows, they're just like old friends. They don't all have the same ability to form columns. Some form beautiful columns, like the Rosa flow. Others don't form columns at all. That's a debatable topic as well. Next one. Ooh, yes. Are they really forming at an angle? No, Tom has just had an inspirational moment. Next one. Thicker. This is the Rosa flow, which was first described by Rosa Dam here in the Yakima River Canyon. You know where this is, perhaps? This is over in Frenchman Springs Coulee on the Grant County side. Next one. This is the Yakima River Canyon. Next one. Don't know where this is, but I like it. Next one. On top of a lava flow, looking at our beautiful polygonal cracks. Next one. And I can't tell you how many times I've been out with people and we look at particular geometries of columns that aren't perfectly vertical, and it's frustrating for me because I don't have an answer. Why are these so squirrely? I don't know. Next question. Babcock Bench near Ancient Lakes. Next one. Those that were with us a couple days ago in Moses Coulee recognize this. This is the Billingsley Ranch at the head of Moses Coulee. 1, 2, 3 flows here. Vesicles at the top, pillows at the base sometimes. More coming on that in just a sec. Next one. You've been to the Columbia River at the Vantage area. Let's cross the bridge. Next one. Here's Route 26, so Vantage is off to the left. We're going to go to Royal City. We're going to get on 26 and climb out of the Columbia Gorge. And this is one lava flow. Here's another. Next one, Bryce. This is the flow top. And this orangey junk at the bottom tells us something about what the land was like when this lava flow came in. Next one. Look at the scale of this orangey stuff. So here's a semi coming from Royal, heading to Vantage. Again, our flow top is here, and almost a quarter of the lava flow is this orange material. What is it? Next one. They're pillow structures. That's our name for them. It's the orangey material is actually obsidian, volcanic glass. This orange stuff was originally volcanic glass, but has broken down or crumbled through time. Devitrified, we call it. And the brown circles, our interpretation, are fingers of lava that went out into water. So the punchline here is, when you see pillows like this, or a pillow structure at the base of a lava flow, you know that the lava flow was fighting water as it was crossing the state. Probably a temporary lake. Next one. How do we know this? Well, off the coast of Hawaii, we've looked at what lava flows do when they leave the island and go into the Pacific. They kind of freak out into these little pillowy, wormy things. So this is lava going out into the Pacific, and we're getting these shells forming with this lava coming behind it. And to us, that's what happens anytime you have lava going into water. Think of the contrast in temperatures there. Next one, please. So each of these guys is one of those fingers. It's not really a circle. It's not really a ball. It's a tube. And again, this was glass where the lava was getting chilled instantly by the water itself. Next one, please. Oh, car keys for scale. Very, very fine detail. There's even some little gas bubbles in here to give us a feeling for the drama. Next one. Okay, I think we're moving to the plate discussion now. It seemed like that was where our energy was highest. Next one. Oh, not quite yet. Can you go back, Bryce? Let's test your skills. You're young. Good. We're to the edge of this flow field. So we can not only teach basalt geology here at Central Washington University, we can also teach stuff out of the basalt field. Where technically is that northern edge of the basalts? The answer is Bryce. Table Mountain. So on a beautiful clear day, it's obvious to anybody who cares to look at this, up at Lion Rock, that's the end of the line for our beautiful, consistent Columbia River basalt fields, basalt lava flows. And once we get north of Table Mountain, we're into significantly older rock. In fact, yes, we're into the old terrain story with Mount Stewart and the paleomagnetism and all that jazz that's much, much older. 15 million, 93 million. So let me give you some professional diagrams, again from the guy who is a hotspot man. So he likes this idea of the migrating away from the hotspot story. Let's see if this works for you. Hey, check it out. Snake River Plain, Yellowstone. We know the significance of that now, right? These are the earliest of the basalts that came out of the fissures 17 million years ago. Next one. The basalt flows themselves migrate north. Next one. Younger lavas. Next one. Younger lavas. There's ages up here. We're all still in the neighborhood of 15 million years ago. Next one. We're starting to flood Ellensburg now. Next one. So those youngest lava flows were kind of wimpy. They didn't have much energy left. So we saw that transition from south to north of the flows themselves. That must mean that the fissures are also migrating with. That's the next set of images. Go ahead, Bryce. The dikes or feeder dikes feeding the Steens. Next one. Imnaha. Next one, Grand Ronde. Look at these guys. They're working their way north as we get younger. Our model needs to explain this the best we can. That's basically a vote for hotspot related. Although if you love your contribution, don't give up. Just keep oh yeah, but my idea was the best, and here's why, and I can explain it. Okay, we can do that over beer later on. Next one. Aha. So, circular features to add to the problem. These circular features are calderas from explosive volcanism. So, of course, our lavas are passive and flood without drama. The Yellowstone hotspot story is one tied with drama, death, explosion, and the point is these calderas young as we get to Yellowstone Park. And if you've been across southern Idaho and you don't remember seeing these, it's okay. They're not at the surface. They're buried by younger lava flows, like at craters of the moon or places along the Snake River Canyon. So to summarize, the hotspot people, initial hotspot activity, and then let's migrate, here's a twist, not only our way, but early indications that there's younging lavas and fissures south, and maybe even towards Bend, which is what we're going to do next. Here we go. Next one, please. So here's taking all the stuff off the map and just showing Yellowstone, Snake River Plain cutting right across these mountain ranges. That was my master's thesis project, by the way, back in the Dark Ages. Here's Kittitas Valley. And so we're on the map and potentially connected to this story. This is an interesting pattern, isn't it? These are the mountains and valleys of Nevada, part of something called the Basin and Range Province, which is potentially related to this as well. Next one, please. So just a couple from this surprising new development, actually in the last 10 years, from Oregon. I'll give you a few diagrams that I grabbed off the internet that basically try to say the same thing. If you look at silicic volcanism, meaning not the basalts, but the sticky explosive lavas that are in eastern Oregon, which is great country, by the way. I don't know if you spend much time in eastern Oregon, but it's remote and beautiful, and the geology is right there in your face. 10, 8, 6, 4, 1, Newberry volcano. That's the younging of the sticky rhyolites in eastern Oregon that really shouldn't be happening if you're a simple Yellowstone hotspot person. Because the plate is moving to the southwest, doesn't make sense to have this if that's all that's going on. Next one. Same message, showing both the younging of the lavas as we go towards Yellowstone and the younging of the lavas as we go towards Newberry volcano by Bend. What is going on? I don't know. Next one. Yeah, just an inventory of lavas over the last 17 million years in the Northwest, not only by age, but by rock type. Let's not worry about it. I don't know what's going on here, okay? So somebody's trying to explain all this. Somebody's trying to model. I think this person likes the Juan de Fuca plate subducting as part of the story and sending some melting to the base. The point is, people are trying to be pretty damn creative to come up with an explanation for the high lava plains, what we're talking about, and the mirror track, which most people feel pretty good about, the Snake River Plain. Fascinating stuff, if you ask me, but I'm biased. Oh, here. So if you're still with it, you want a hot spot and a moving North American plate, this should feel good to you. Hot springs galore, by the way.
Is this current heat?
This is current heat, yes. Next one. Just to point out that our fissures here are inland of our Cascade volcanoes from last week. Subduction related for these guys, we really can't connect the subduction with our fissures. We need an independent source, whether that's a hot spot or a clockwise rotation or meteorite, all those things as possibilities. So to Yellowstone Park quickly, just to remind ourselves, that's where the hotspot is currently located. Next one. We all know where Yellowstone is. It's in Wyoming. So currently in Yellowstone, there is a caldera from the last explosion, which was 600,000 years ago. It's been 600,000 years, and the last 3 explosions forming calderas have been every 600,000 years. So there's another one of these cycles, and it looks like if the pattern is holding true, we might be in for some interesting action down the road, but probably not in our lifetime. Next one. Yellowstone Park and the Snake River Plain. Keep going. We've got about 5 minutes left of this stuff if you can hang in. Here's the stationary hotspot and the moving North American plate. These are centimeters per year. So the North American plate's moving roughly 3 centimeters a year over the hot spot. We talked about that a couple weeks ago. The movement of the Pacific plate over the Hawaiian hot spot, 3 times as fast. So the spreading of the East Pacific rise is 3 times as fast as the spreading of the Mid-Atlantic ridge. There are other hot spots around the world. We don't patent hot spots. There are other places in the world, less known of them, at least for me as a biased American. Next one. So the hot spot has created not only the Hawaiian Islands, same idea in Hawaii then. As you get away from the hot spot, the volcanic material is going to get older. But if you suck out the water of the Pacific Ocean, you realize that that trail goes all the way to Russia. Next one. And as the volcanoes get moved off the hot spot, they quit erupting and slowly die, and eventually get reduced to a seamount, which is a mountain underwater. A little animation of that. Let's try it for fun. So stationary hotspot. This can work for Yellowstone or Hawaii. Is this what you had in mind? Stationary heat source, moving plate, only one active volcano at a time, and the deposits are going to get progressively older as we go down plate direction. The only thing we'd add to this picture for Yellowstone is we'd have thicker crust, we'd get rid of the water, and we'd have explosions instead of quiet shield volcano building. And here's our calderas in millions of years getting progressively older until we get down to the end of the line. Next one. Image from space. Check out this. Beautiful scar. And then this is a younger feature that does not appear to be part of our story, even though it's tempting to use it. Next one. Can you go back for a sec? Did you look at here? Look at how unusual we are for the American West. We've basically loaded the crust with those lavas and depressed the crust. Our elevations are low. Look at the Weather Channel. We're always a little bit warmer than everybody else, right? Because of those basalts depressing our crust. Okay, quickly, some images to put a little frosting on the cake. Very recent geology, and then we'll quit. An image 15,000 years ago of the Puget Lobe, the Okanagan Lobe, the Purcell Lobe, Glacial Lake Missoula, Glacial Lake Columbia, if you can see the fine blue. And Glacial Lake Lewis is not on the map, but when it was full of water, filling areas by Pasco. Next one. Here's a quick synopsis then. When we finally break the Purcell Lobe, the water is cruising across eastern Washington, heading for Wallula Gap, and scouring the landscape upstream of that. Next one. Satellite images from NASA, where you can see the flow paths. The scale of these Ice Age floods are best viewed from that distance. It's like a braided stream channel in Alaska. Next one. These are also from this space shuttle or something like that. Something up in space. Next one. A little dark. Can you see where the floodwaters happened? Here's Grand Coulee. Here's Moses Coulee. Here's Saddle Mountains. Next one. Wow, gaudy images. Same idea. Flood paths. Next one. I love these images. I've showed them to you before a little bit. Just spectacular, showing where the floods hit and where they missed. Notice how Kittitas County looks so different than this, mainly because we were not hammered by the floods. Next one. Moses Coulee, if you were with us on Sunday. Next one. You got to really know Eastern Washington and love it to know some of these towns. Oh yeah, up by Wilbur. Oh yeah, I got you. I know where you are. Really? Next one. Washtuckna? Oh sure. Yeah, good people there. Back at ground zero where the water's accumulating, there's actually shorelines from that ancient glacial Lake Missoula. Next one. Tom Foster photo. Campus of University of Montana. There's the big M on the hillside. And by God, we've got ancient shorelines of that lake. There's murmuring in the crowd. I'll take that as a good sign. Next one. Interesting thought. And when I first came to Ellensburg, I didn't really believe or understand that the floods ripped up so much rock. I just didn't get it. I get that the floods happened, but wouldn't they just polish the surface? Why are you literally creating a coulee from scratch? And then I started learning more about the basalt and the heavily fractured nature of basalt. The rock is pre-cut, essentially. It's ready to be hauled off. And what if Eastern Washington was all granite? I don't think we'd have the coulees that we know. I don't think we'd have all these chasms, all these gashes in the landscape. I do think the floodwater would just cruise over the surface. So it's a combination. That's what we're trying to do tonight, realizing it's this magical combination of these lavas and the floods to create this dramatic plucking of the rock away from the countryside. Next one, please. Right, so we're looking at the details of these cooling structures. Next one. We can see the granite doesn't really have that. Next one. And so the rest are just spectacular photos from Tom. Look at these walls, my God. And the reason is the waters can cruise through there and just pull those columns away, haul them away. Easy work. Next one. Next one. You know where that is? It's not. It's Frenchman Springs Coulee. So here's the old Vantage Highway. We're heading west on the Vantage Highway. Used to be able to cross the river and then head towards Ellensburg on the Vantage Highway. This is Frenchman Springs Coulee. These are where the climbers climb. These are all the guys tenting there. Next one. Beautiful. Dry waterfalls here. Cataracts. Where'd all that rock go? Downstream, plucked out by the floodwaters. Why? It's pre-cut and ready to haul. Eastern Washington, potholes here, caulking going on, all sorts of dramatic geology. Go ahead. A little dark, let's move on. Crab Creek, Saddle Mountains, even some flooding in Crab Creek. And here's a little stubborn piece of a lava flow that didn't want to get taken away. This is not an erratic, this is in place, But there was a lava flow crossing this whole area. Most of the lava flow was taken out. That guy didn't want to go for whatever reason. Next one. The big giant current ripples at West Bar. Next one. A boat for scale. 100 yards between crests of these ripples. 40 feet high, each of them. Wallula Gap, where the water is trying to get to the ocean, can't by the Tri-Cities, so it's this constriction that's responsible for some of those secondary temporary lakes. Next one. I know I said 5 minutes, right? Give me 3 more, would you? So here's an interesting diagram created by Bruce Bjornstad of the Tri-Cities area. Can you see here's the freeway? This is an actual photograph. Kennewick, Richland. But taking all the erratics, or the rocks that have been left by these floods that are scattered on these hillsides, we've been able to reconstruct that the tippy tops of Badger Mountain and Candy Mountain were not completely flooded, but at the maximum of Lake Lewis, everything else was under a serious amount of water. So that's not an idea. This is carefully reconstructed. Maximum height, 1250 elevation above sea level, down at the Tri-Cities. Next one. Some painting done the same thing. This is what Vantage would have looked like with glacial Lake Lewis time. And the concept for these big rocks being dropped is that they were rafted in here by ice, icebergs. Next one. So you find these rocks sitting out where they shouldn't be, big enough that they were probably not just brought in by the flood water. They needed a little bit of help with the raft of ice. Next one. More. Keep going. Yeah, keep going, sure. I went to graduate school here in the late 80s, and I was focused on the Snake River Plain and the lavas, but an equally impressive story that I didn't care about that much at the time, but I now do, is the Lake Bonneville flood story. And if you do go to Pocatello down the road, there's a great eating spot. Go ahead, Bryce. Buddy's. It's family owned, been there forever and ever. It's a tradition to just show up when you visit, so remember that. Buddy's in Pocatello, Italian food, outstanding. Next one. Here's just a quick map. Glacial Lake Bonneville, eventually too much water, flood into the Snake, and get that water all the way to the ocean. Next one, please. Same idea. Glacial Lake Bonneville, flooded over Red Rock Pass, and then down the Snake River. Next one. So this is the Snake, and if you go to the Snake, any place in southern Idaho or in Hell's Canyon, you can certainly look at the river and the lavas, but there's also scattered flood boulders everywhere from Bonneville. Next one. 15,000 years ago. Next one. How about that? Those are all boulders dropped by the floodwaters. Bonneville floodwaters, 15,000. Next one. Next one, please. We don't really have these in our area, these heavily polished erratics. Different story there, different volume. These are all flood gravels here from Bonneville. Next one. In Hell's Canyon itself, this is the last slide coming up next. Bonneville flood deposits, Missoula floods on top. Most people ignore the deposits and look at these dramatic coulees and things like that, but this is a big part of the story, and if you really want to understand the flood history, it's the deposits that are going to yield more information to us down the road than the scars themselves.
Where was that taken?
This is in Hell's Canyon. That's about a Pittsburgh Landing in Hell's Canyon. Thank you for coming out tonight. Appreciate it.